Well, I want to thank everybody for coming, and just looking at the clock to make sure I don't go over time, because I know the one thing that you have to be excited about is a statistician talking, right? I mean, what more exciting thing can there be than someone who studies statistics and also likes long distance running and swimming? I mean, those two things together. So I'm currently, we're all, not just myself, because I know many of you are excited that the Boston Marathon is currently going on, and I was watching it right before I came, and I've often told people, if you're the sort of person that likes dealing with computers and numbers and long distance running, then you're always people's favorite to show up at a cocktail party or stuff like that. But what I want to do, I kind of have a twofold purpose this morning, and the first part of that is to just talk about what I do a little bit. Oftentimes people are surprised that statisticians do research and we have an area of our own, and so I want to talk about that for a few minutes. But then I think more importantly, and I hope maybe more useful for you all, particularly for students, and I really appreciate students coming, is talk about kind of what my experience has taught me. And it's not that my experience is better or more informative, but I've got the podium for 20 minutes, and so I can, I guess, talk about it. So that's what I want to do. But like I said, first I'll talk just a little bit about kind of what I do and how that fits in with statistical stuff. Bob's already told you, before I came here I was a consultant, and that'll play into some things I have to say later. I think that's just a lot of fun to look at, isn't it? That's kind of the nightmare scenario you probably had. It's like I've got to sit and listen to a statistician for 20 minutes, and it's going to be slide after slide just like that. But actually not too many. So item response theory is one of the things that I do, and that's actually was my dissertation topic, was in that area and stuff. And so I feel like I got to talk about it. And actually that equation tells a very interesting story. And that's what got me interested in and excited about statistics, is the idea that these equations that then produce curves or graphs like that or numbers that we can use actually tell a very interesting story about the world and the way that the world works. And so that's really what gets me excited about statistics. And I can tell you in all honesty, I'm really excited about it. I'm excited to come to work every day. I look forward to it. And it's in part because of stuff like that. So item response theory is essentially a way of understanding how people respond to test questions, to survey questions, to attitude questions, and understand it based on the person, which is the little theta there, as well as information about the items, the A, B, and the C. And so with that, I could give you information with that equation and the numbers that actually fill in those values. I could give you information about my ability to do math or my level of depression and anxiety. And I can also tell you how well a given item on a test or an instrument does at telling you if I'm depressed or anxious or really good at math. And I think there's something kind of cool about that. And now I think it's probably the point at which I'm starting to lose people, right? It's like, okay, all right, this is what we were thinking it would be. So what do statisticians do? What do I do? Well, what I do is I take something like that someone else came up with a long time ago, and then I test it out on different kinds of data. So I write computer programs that generate data, so I don't have to, as I said in that video, I don't have to get my own folks. I can just write a computer program and boom, I've got 1,000 people ready to take a test. And then I test it out. I test out this equation under different conditions. And if it doesn't work under certain conditions, then what I'll do is I'll say, well, I wonder if there's a better way for us to estimate that B. There's a number that goes there. That's called item difficulty. And I wonder if there's a better mathematical way to estimate B. And so I play around with the computer a little bit and try out maybe 2 or 3 different methods for estimating B, and then see which one works the best. So that's what statisticians in large part do, is we take real data problems, real issues, and we try to do a better job of understanding them through numbers. And if we don't have a good tool today, then we try to develop one. So my grandfather, my dad's dad, was a tool and die maker in Chicago in the 20s and the 30s, and so I figure we've kind of come full circle, right? So he made tools that people used in the 20s and 30s, and so now I have, that sounds a little pompous, but I could say now I have the excitement of making tools, for the new century, and so that's what I do. So that's item response theory. And then you can extend that, and so one of the things that I've gotten interested in is, well, what happens when you've got 2 or 3 groups of people, and you measure those people on, let's say, math ability. But the items don't work the same for all the different folks. Well, that's a problem if you're taking a test, because if I'm a male and I'm taking a math test and that item doesn't measure math the same way for me as it does for someone else, then my math score might not be representative of my ability to do math. Restart. Yeah, that's right. You might as well. You got 14 minutes, buddy, and then it's all over. So, thank you very much. So one of the things I do is this differential item functioning, and all that means, all that is saying, you know what? Let's see if we can figure out if items don't behave the same way for males as they do for females, and why they don't. And then I can help folks who are teaching or folks who are developing tests improve them and understand which items aren't working and which items are and why they're not. And then that's kind of neat, I think. It's fun. At least for me, it's kind of fun. So that's measurement invariance or differential item functioning. Does the test work the same way for different groups of people? And then along with that, I've been interested in this business of prediction for a long time and sort of predicting outcomes. And this is an example of what's called a classification and regression tree. It's more generally, these are called recursive partitioning algorithms. And you all are probably thinking, well, what's that? Well, actually, you're intimately familiar with recursive partitioning algorithms, or at least their byproduct, if you use Netflix. Because Netflix uses algorithms just like this to predict what movies you'll want to watch and how to advertise to you. So you pick a certain movie and you start picking a lot of action-adventure movies, and pretty soon they've got an algorithm like this, and some nerd like me is sitting at a computer and typing stuff in, and they're predicting, well, you know what? If Holmes likes action-adventure movies, he might like this new one. But he's probably not going to like this romantic comedy. And so that's what recursive partitioning algorithms are all about. And what I'm interested in is using them and improving them to predict outcomes in education and psychology. So, for example, if we give students a bunch of formative assessments, a bunch of tests, can we predict which students are going to, next year, have difficulty in passing the state standardized test? Or which students are going to have, be more likely to drop out based on that? Which individuals are more likely to have a certain neuropsychological problem or issue? And we can do that fairly effectively with these tools. And so, again, I'm interested in how do we make these tools work better? How do we make them work with small samples and with unusual groups, people that perform very differently on these instruments? So, and then finally, stuff that I've been working on lately, generalized additive structural equation models, sort of puts together data mining with I call it that, but it's not like I made it up, but latent variable modeling or structural equation modeling. And so in this case, a question of interest might be, well, if I know or if I believe that the relationship between, say, anxiety and test performance is not linear, in other words, it doesn't go straight up or straight down, which is probably true, how can I estimate that relationship? And these generalized additive models and applied to latent variable contexts, that's what they do. So working with kind of 2 different statistical paradigms, I've tried to come up with a way to model that relationship, that nonlinear relationship there with a computer. So, and again, how do we do that? Well, we take equations other folks have come up with, we apply them to a new situation, we tweak them a little bit, we write a computer program that generates data, and we test it out and say, hey, did it work or did it not work? And then we figure out where it didn't work and move on. So that's kind of what I do for fun. And it is fun. I really enjoy it. What I'd like to do now is to spend the last 10 minutes or so of my talk sort of sharing with you a few things that I feel like I've picked up along the way, either from my own experience or from working with researchers at Ball State, at the University of South Carolina. And in particular, I hope that some of my insights, be it kind of narrow and shallow, might be helpful to students in particular and to folks who are interested in going into academia or fairly new in academia. And I do want to emphasize, it's not like I think I've got all these great insights. It's just I've got the time. I'm here. You guys are here, so let's just do it. Yeah, currently, that's right. I've still got 10 minutes to get you out. But you know that Dr. Turcotte is coming up next, and she's going to be a lot more exciting, so if you can hold out. Well, like I said before, and I hope it comes across when I talk about it, but I just think research is a lot of fun. It's all about discovering stuff and learning new things and figuring out how a little slice of the world works, and that's really cool. I mean, if you liked school when you were in middle school and high school, and if you like learning new things and reading new stuff, I mean, research, that's what it's all about, and that's what it certainly should be about. And one of the things that I have tried to, for myself, try not to lose is that sense of excitement about figuring things out and not lose the overall goal of research, which is, I wonder why that is the way it is, whatever that is, whatever the thing is that you're studying. And I think that, certainly that's why I ended up getting a PhD and going into academia, and I hope that, I think that's why many of us do. So it's fun, but it's also a lot of hard work. And one of the stories I haven't really told students, because I don't want to scare them away from doctoral programs, but I think it's worth mentioning, is my own experience in being sort of given my dissertation topic. And so at the University of South Carolina, we didn't really have we didn't have the choice of what our research topic was going to be. We would choose an advisor, and the advisor would say, well, here's what I'm working on. Well, I had somebody on my committee who said, why don't you do an item response theory analysis of some test data we have here in South Carolina. It's a standard analysis, and I thought, great. I've been doing analysis for people for 13 years, and that'll get me out of here fast. I can do the whole thing in 6 or 8 months, and I'll be done. And then my advisor said, no, that's not what we're going to do. So he told me, well, what I want you to do is I want you to do a simulation study in so write these computer programs in kind of a new area that I don't know much about, but I want to learn about. This is the advisor telling me this, right? So it's like, well, I want you to do it so I can learn about it. And I'm like, okay, all right, that sounds like fun. He said, but the first thing is you got to learn Fortran. Fortran, the computer programming language. And I'm like, well, I don't know Fortran, Brian. Oh, no, I know you don't, but you will by the time you're done. And so here I am. Well, the first year of my 3-year odyssey to write a dissertation was learning Fortran. And I was not a happy camper, as you might imagine. I thought about dropping out. I was like, man, this sucks. I mean, I don't want to do this. What do I need to do this for? Well, it turns out that my advisor had a lot of insight, because had he not forced me to do that, had he not made my dissertation experience arduous and long and hard, I would not be standing up here today boring you to death. I would have done an easy analysis that I could have done in my sleep, because that's what I did for a living at the time as a consultant. I would have walked out the door of the University of South Carolina with a PhD, with not a lot of effort on the dissertation, and I would have been stuck. I wouldn't have had anywhere to go, because statisticians don't really get paid to just do, our research isn't just doing analysis on existing data. We got to do something new. So the fact that I was forced to do this really pushed me into things that I didn't think I could do. I learned things I didn't expect to learn, and it was worth it. Didn't seem worth it at the time, but it ended up being worth it. So I think that's true of research in general. It's hard. And as someone who likes distance running and likes swimming and stuff, I like stuff that's boring and hard. What can I say? Failure is to be expected. So last Sunday, I finished my run at Mounds. I get back to my car. It's a beautiful day. I had a great run. I take out my iPhone. I look at an email, and I have an email from a journal editor for a paper that a friend and I submitted 3 years ago, and it's in its 3rd revision. 3 years. So we thought, well, surely, 3rd revision, 3 years, that's going to get accepted. It's just a matter of time, right? So I happily open up the email thinking, well, here's the acceptance that Brian and I have been waiting for. Dr. Finch, we are very pleased that you sent your manuscript to us. And whenever a letter starts that way, it's like, well, you know what? It's a kiss-off. It's nope, this is not going to happen. And sure enough, it didn't happen. After 3 years and 3 major revisions, we were told no. And I'm like, really? You just ruined my day, Mr. Editor. But the fact of the matter is, we thought stuff worked, the editor thought not. And that's just part of research. How many studies have many of us done where we started doing something, we worked on it, and it just, it didn't pan out. And we spent 6 months trying to do something that in the end we couldn't get anything for in the context of academia. It's just a lot of work, and you have to expect that sometimes things aren't going to work out. Good stuff's not always going to happen. And that's why when we get to the last slide, hopefully I'll be able to turn everybody around and we'll all be excited about research again. One of the things I didn't realize as a student, oh no, okay, no, I'm sorry, I was ahead. So research success can come in unexpected ways. Just a very quick story there. One of my simulation studies, I had to tabulate results by hand, and you can imagine how much fun that is, sitting in your office with a calculator, adding up numbers and putting them in a spreadsheet. So that's what I was doing. But I kept noticing this really weird pattern. So this is kind of like my story about my advisor. I noticed this odd pattern in the results, and I'm like, huh, that's weird. I wonder if I wrote the program wrong. So I went back and I checked my program, and no, it seems right. Well, it turns out the odd pattern was an odd but real pattern in the data. And what made that cool, besides the fact that I was able to get a publication out of it, is that we discovered something really neat about this particular statistical method for detecting differential item functioning. It was kind of fun, but it was unexpected. I didn't expect the result, and I didn't expect to find it the way I did. I was just slogging through with a calculator, adding up numbers by hand on a Friday afternoon. So my advice would be to always be open, to expect that unusual things might happen, and that results that we thought we'd find, we may not always find, but we might find new stuff, and stuff that nobody expected us to find. And a lot of that goes back to the hard work thing, unfortunately. So this is what I was going to talk about a second ago. So one of the things I did not appreciate fully while I was a student is just how much my professors knew. And this is not to say that I know a lot as a professor, but it's to say that as students, you have a once-in-a-lifetime opportunity to work with folks who are experts in their field. And I didn't really take full advantage of that. I was in the mind of, well, you know, I've got a child, I'm married, I need to get done, I need to get moving. And I didn't really realize until I got out that, hey, you know what? Those folks knew a lot. And there was a lot more I could have gotten from them if I had just taken the time. And so one big piece of advice I would have for students is remember that the folks that are teaching you are really experts. They know a lot of stuff. And at least we know a lot of stuff, hopefully, in our field, right? And so that's a resource that you don't want to lose track of. You don't want to lose sight of that fact. Because once you leave, then you become the expert. And once you become the expert, you don't have that luxury necessarily of saying, hey, so-and-so walking down the hall, and so is there to give you advice and tell you stuff. So definitely I'm moving on just because I don't want to take up any more of your time. I think one of the things that the Stat Lab experience did for me, the consulting experience, was to expose me to a lot of statistical stuff. So I had to learn a whole lot about a whole lot of different things, because I'd have somebody walk in the door from marine science and they had one problem. I'd have someone walk in the door that afternoon from economics and they'd have another problem. And so I had to learn a lot of different things. And I think that in the end was really good for me. I wouldn't have done it on my own, but I did it because I had to. And that cross-pollination of ideas has informed my practice and my work since that time. And I would definitely encourage all of us to stay open to learning new things. And I still try to do that here. Never thought I would know, for example, all the different ways that Dr. Davis can do neuropsych assessment. And now I know all the different ways that Dr. Davis does neuropsych assessment. I didn't know anything about neuropsych assessment, and I probably still don't, but I can at least talk about it like I do, right? So I can, well, I'm not a neuropsychologist, but I work with one, and as a matter of fact, I can tell you from the way you're acting that, and by the way, my name is Dr. Andrew Davis. If you have any questions, I just want you to know that. So definitely keep yourself open. I try to do that. I'm not always successful, but I definitely think that's important. My favorite quote from a friend of mine, I just had to put it there. My poor students hear it every semester. It is probably the credo of most statisticians. What works, works, and what doesn't work, does not work. I had a client once in the Stat Lab who learned one statistical test. That was the t-test, one of the very first tests that you do. Every problem that this particular individual dealt with was a t-test problem. Didn't matter what it was a t-test problem. Even if it didn't work, he tried to make it work. And so what I would say is, make sure that our data guide our theories and not the theories guiding the data. In other words, sometimes things don't work out the way we expected in terms of our results, but that's just the way things are. And that's, again, part of the excitement of research. And finally, Success is based on whether you learn something new. It's neat to get publications, it's neat to get awards, it's neat to do all these things, but in the end, research is about learning, and learning is about understanding your little piece of the world a little bit better. And if you lose sight of that, I think, if I lose sight of that, I think what happens is you become too tied to the extrinsic products of research, and that takes the fun out. And if it's not fun, it's hard for me. It's kind of like running. I tell people, if you don't like running, don't try to run a marathon, because running a marathon for someone who likes to run is awful. It's terrible. It's an awful experience. So if you really don't like running, just don't do it. And it's the same with research. If you don't like research, if you don't like that sense of pushing yourself to discover new stuff, it's just going to be hard. It's going to be miserable. And it's not for everybody. But if you do like it, don't lose sight of the fun and the excitement that I think comes from that. So I just want to thank you so much for your time and attention, and I guess we're open for questions. So if y'all have questions for me, I will dodge them as best as I can.
I'll ask a question.
Sure.
Oh, hang on.
I'm an English major, so just forgive the obvious question to me.
Yeah.
When you say you write a computer program to get data about how things happen in the real world,
yeah,
what do you mean by that? How can you write a computer program that will give me like a real person kind of data?
Well, that's a great question. That's a great question. So the idea is, how do I write these programs? Well, let's take the example of the test, the item response theory. So we're talking about test responses. So what we do is we say, all right, well, we've got lots of testing data around. I have some, I have friends that have some, and these are representative of the general population taking a test. So we can get all those item parameters, that A, B, C, and all that stuff in that equation. We can get estimates of those from pretty big samples. So I'll write a computer program, and I'll say, all right, generate data for me, computer, that has items that have those A, B, C parameter values. So those numbers for how hard the item is, how well the item picks out good math folks from bad math folks, how likely it is you might get the item correct because you guessed at it, as well as how good people are at math. So I'll write a program that generates data that looks like that, and I throw in a little randomness, because obviously if I made everybody the same, it wouldn't be realistic. So I say, let's assume that we have people that come from a certain type of population and certain kinds of items. Let's throw in just a hint of randomness, and let's generate a data set. And so we'll say we'll have 1,000 test takers that look like that. And then I'll run that item response theory program on that data. And then I'll do that again and again and again. And I might have 1,000 data sets of 1,000 people, and each data set I run the analysis on. And then I say, well, my interest in this case is how well does the computer estimate the difficulty of the item? So that's that B number. So I say for every one of those 1,000 times I run the program, I save the value of B. And I know what B is because I told the computer, generate the data with a value of B equal to 0.2, let's say. Well, how close to 0.2 is the average B value across all those 1,000 folks? And if it's really, really close, then it's like, hey, that worked pretty well. If it's really far off, if the average is like 0.6, then I say, you know what, that didn't work too well. So the way I estimated that B value is wrong. It's not a good way to do it, and I got to go back and figure out a better way. So I don't know if that helps, but that's basically what we do. Yeah.
What has been the least useful statistical method that you've actually used?
The t-test. The t-test, because the t-test is almost never, for those who are not familiar, the t-test is just a way to compare averages for two groups of people. And so there's so rarely a case where you only have two groups of people that you care, or two groups of anything that you care about, and even less useful that you have one thing that you care about and you compare the mean of that one group to some other mean. So because it oversimplifies. And that's always a danger with statistics. And one of the things we have to watch is that, we create these models, and George Box, a famous statistician, said all models are wrong, but some models are useful, and he was exactly right. So, these models are oversimplifications of how the world works, and we know that. The question is, are they good enough to give us insight, or are they so oversimplified that it's just a waste of time? So the t-test would be my answer.